Hello and welcome. My name is Nepogodin. I am cloud architect, and here with me are colleagues of mine, Bhanu and Atrash. We are from Dell. And today we are going to talk about our journey on redesigning our pricing platform, redesigning, reshaping, refactoring, etc. It is not going to be about machine learning, data science, or data analytics. It is more about our traditional way of handling data, handling large amount of data in a data store, which we used. We're going to cover some of the challenges of our legacy architecture, the way we decided to address those, and most importantly, what type of technologies we had to leverage to achieve our objectives. Spoiler alert, it's going to be Neo4j. And we are going to discuss pretty much our decision-making process, how we come up to the current architecture, but all squeezed in time within 30 minutes. We're going to cover some of the findings that we discovered along the way, as well as some of the our operation model, and a little bit of statistics about the volume of data that we are serving. And at the end of the session, perhaps we will have some time left for questions and answers. Dell Digital is a set of services and infrastructure created to serve a Dell commerce platform. By itself, it comprises of various umbrellas or various domains, such as quote, payment, order, product, and price. Today we are going to focus only on the price. But each of those ecosystems or each of those domains is their own large set of tools and services, starting from legacy one and ending with modern cloud-based one. However, the entire process of replacing legacy solutions with the newer ones, we are referring to as the digital transformation. And that digital transformation allows us to create a unified operating model. And unified operating model, it creates ground for kind of horizontal scaling on the corporation level. And let's quickly dive a little bit into the history. The time when a service-oriented architecture was a dominating golden standard of any enterprise solutions, or many enterprise solutions. Many of you at some point in time have dealt with one of the variations of enterprise service bus architecture or implementation. There's many commercial and custom solutions, but the main principle is the same. There is an orchestrator or set of orchestrators who are responsible for gluing together disconnected sources of information. Once the data is obtained, orchestrator can act upon and pass it over to the caller. However, the challenge of that problem of that architecture is that despite the fact it was a great advancement in comparison to monolith, it had own disadvantages. A typical request might look like this. A customer would initiate communication with the commerce service. Commerce service would start talking to the backend, and backend acts as an orchestrator. An orchestrator would initiate sequential or parallel communication with external data sources. Once all data points are obtained, the data is passed back to the caller. However, as it usually happens, the reality is not as bright as it looks on the diagram. Should one of the dependency services fail or simply being unhealthy, the entire response is compromised, either from SLA agreement standpoint or in the worst case scenario cannot be complete at all. Of course, each of those challenges can be addressed with some sort of architectural changes, architectural improvement, but all that is coming at the expense of complicating the architecture, or complicating the solution. And we all know the simpler the architecture, the better it is. So what would be the natural step in improving runtime request experience? Well, that would be eliminating runtime dependency on the external services. But we still need data, right? The answer would be to make data available without a need to make a trip to the external dependency services. And that's where a serverless or event-driven architecture becomes an attractive option. Instead of making runtime requests, we make data available ahead of time, so that during the runtime request, the entire request is served by a self-contained package that has all necessary information to make a decision and to provide the response. And preparing of those packages can be referred as denormalization. What previously was called as what was previously served as by online orchestrator is now addressed by offline consolidator. However, the main advantage is that offline consolidator is not a subject of runtime SLA agreement. Therefore, it can afford longer processing time or even period of unhealthy upstream systems supplying the data. Since we mentioned denormalization, let's quickly look at two different flavors of that concept. Foundation of any commerce platform is the price of the product, of course. And price of a product is typically presented in some sort of pricing document. And that pricing document has some number. But to get that number on the screen, there is a complex business and procedural logic behind. For the large retailers like Dell, setting individual prices per individual product would be a highly inefficient process. Instead, prices are formulated based on targeting certain properties, attributes, or classifications. And once all data points are obtained, we can generate that pricing document, and from that pricing document, we can display our price to the customer. However, Dell has own specifics. Dell allows for possibility of customizing the product. Therefore, price of the default configuration may not be suitable for the custom configuration. And the immediate temptation would be, okay, let's generate pricing documents for every possible configuration. But the challenge is, again, some of the Dell products allows for several hundred of configuration options. And with the simple math provides an interesting fact. Just 30 multi-select configuration options result in more than 1 billion permutations. And billions of documents, and that's not probably what we want to store even in the realm of big data. And that model, when you have a single product, for a single product, you give a single price within the particular context, is called pre-compute. Typically, product at Dell is presented in the form of a tree structure. There is a product, which is a root node itself, which comprises of various modules, such as memory or hard drive. And each module comprises of different configuration options, like you can choose 8 gigabytes or 16 gigs of RAM. And product has a default configuration, and default configuration has a default price. If default price was the only one required, we could easily go with our pre-compute model and store prices in our denormalized store repository. However, as I mentioned, Dell allows possibility to customize the product. A customer may choose, I don't want 1 terabyte drive, I want 2 terabyte. As you can imagine, 2 terabytes is more expensive than 1. Therefore, the price for the default configuration is not applicable to the custom configuration. Again, temptation might be, okay, let's create all possible combinations in the selection. But again, that can quickly go out of control as the number of configuration options gets increased. Instead, what we want and what we applied on our practical level is that we create a lightweight association between product structure and price-forming elements. What I mean by price-forming elements is that it doesn't have to be a number. It is just a mathematical abstraction. It could be subtraction, deletion, multiplication, or non-linear tier-based logic. The important thing that once we have that association available, resulting price is coming as a result of applying those mathematical abstractions on top of each other. This way, we get lightweight calculation in memory. Still denormalized content, still no dependency on the external packages, but everything, but the end price is coming as a result of mathematical operation. That's what we refer as a pre-assembly model. To present price of the product, Dell needs 3 main pieces of information. Product structure, price-forming element, also adjustment or price mutator, and component, which is pretty much data enrichment mechanism. Each of those are living in their own ecosystem with little to no correlation to each other. However, changes in one system has an avalanche effect on other ones. Just to give you a simple example, memory stick, 8 gigabytes. It has own price, it has own cost. If down the road, and that memory stick can be used in thousands of different products. If down the road, business decides, okay, now we give 10% discount on that memory stick. What's going to happen? Thousands of different products will be affected. However, the relationship between the two, between the product and the adjustments is not determined ahead of time. As a matter of time, it's not even known. To preserve or to create that model of relationship or association between product and adjustment, we need some medium. So we can formulate the question, what do we use as a service as our gluing mechanism from which we can generate our denormalized data content of pre-assembly model? And the answer is graph. In our case, Neo4j. Effectively, Neo4j has become a centerpiece for our data consolidation mechanism. And denormalized content is nothing more than graph traversal result. But why graph? Why not relational DB or some other NoSQL DB. And the answer lies in several factors. Probably the most important one is the fact that in order to achieve that, maximum efficiency from the pre-assembly model, the relationships between price-forming elements and product structure has to be the simplest possible, in the form of one-to-one relationships. However, data are not authored that way. Data are authored different way. And very rarely business author data in that one-to-one relationships. More often than not, it is some sort of sub-tree relationship of various depths, non-deterministic depths. So whenever we are resolving that type of relationships, not only we have to hop number of times, and number of hop can be anywhere between 2 to 7, but in addition to that, multiple conditions have to be met in order to satisfy that type of relationships. In terms of data processing, we were aiming at two major goals: no proliferation during intake time and denormalized output. And in terms of data representation, which is kind of subjective factor, but it was important for me, to a degree, Neo4j or Graph allows natural data representation. And what I mean by natural is that by looking into your data and navigating from your vertex to edge, you should be able to formulate meaningful sentences in plain English so that you would understand what the data means, and you would be even explain that to some outsider. Data density problem. Whenever two data forming, price forming entities arrive to pricing engine, they have own life cycle, and the relationship between the two are not known. But during the runtime, we don't want to spend our time, we don't want to spend intake time on resolving all possible relations. And even less we want to spend our time on duplicating that event to reach to every possible destination. Instead, we create a point of potential contacts, because lifespan of each of the events has non-deterministic nature. Sometimes product may arrive first, sometimes adjustment may arrive first, sometimes companies may arrive first. But to create the possibility for connecting with the cheapest possible traversal, we create abstractions called context nodes. Those context nodes don't belong to any particular data type, but using declarative syntax, we can explain to our model what can be used as a context node. Then later on, those context nodes are serving as a main consolidation point. Just to give you a very simple example, two products arrived at some point in time. Both got connected to some context node. Later on, adjustment arrived, and to a single connection to that context node, we get the possibility to traverse or associate that adjustment with two different products. Data Dell are authored at different grouping level. Sometimes it could be business catalog, sometimes it could be customer catalog, country segment, or any other grouping mean you can imagine. And often those grouping factors are non-linear or non-hierarchical in its nature. As a matter of fact, more often than not, those are more of a forest nature with possible and quite frequent circular dependencies. And in realities of graph, we can afford that non-linear dependency and abstract it out. This way, when a new event arrives, we don't want to spend our time to proliferate against all authoring scopes. We associate that event with the forest, and that event or that data becomes available to the entire forest. And despite the fact that we have all price-related information stored on graph level, we don't want to spend our runtime on executing the traversal. The reason being is that, as I previously mentioned, to achieve maximum efficiency from pre-assembly model, the relationships has to be the most simplistic possible, in the form of zero to many relationships between product structure and price-forming elements. And this is done by preparation. Instead, we want to have during the runtime, we want to have a self-sufficient data content that has all necessary information to execute that light just-in-time in-memory calculation. But to preparing of those packages is done via scalable background processes, which are not subject of runtime SLA agreement because they don't participate in the runtime request. All they do is prepare data ahead of time. In this regard, what is important is not how much time we spend per package, but instead how many packages we can generate within a given time. To give you a simple example, if we spend 800 milliseconds to prepare a single package, doesn't sound too impressive. However, if within the same 800 milliseconds we can generate 10,000 packages, that's already not that bad. And pricing engine in its nutshell is nothing more than a calculator. It calculates price for any product that can be presented in the form of tree structure. It calculates price from the leaves to the root, from root to the leaves, or anything in between. In addition to that, it solves common commerce platforms, such as rounding, compensation, or currency conversion, or business problem, delta price. From the given selection, if I select something new, how my price would be changed. Or price explanation, how did we get to that price point? Or price breakdown. What is my relationship, how I can break my price into what is the discount, what is tax, what is shipping, what is cost, etc. And while we are analyzing a variety of cases among Dell internal customers, we quickly realized that implementing use cases, we cannot afford it. And the reason being is that despite the fact that the platform was created for serving only Dell, number of cases and number of variations among Dell internal customers is no different than serving external customers. All that means that we couldn't afford any hard-coded use case implementation, because use case implemented for one customer most likely will not work for another one. Therefore, we had to adopt SaaS principle, software as a service. This way, we don't implement use cases, but we provide capabilities. And then the customer pick and choose which capability they want to use to achieve their objectives. And while working on the SaaS platform, we had to adopt a very strict set of rules. I can give you just a couple. For example, pricing does not mutate data. It only serves data. All that means that we don't give any interpretation or meaning or assumption about data content. It's all up to the upstream system to decide how data must be represented. Or it is up to the model declaration, where the customer would explicitly has to declare how data has to be processed or interpreted. Or another rule, which is my favorite. If we implement that feature and we put it on the market, will we be able to advertise the feature as our selling point? And while it sounds like a simple statement, in fact, it helped us to save from many cases of temptation to create something quick and dirty to accommodate some customer. The answer is usually no, but we can provide you with the capability that you will be able to reach down the road, and other customers would be able to do the same. And let's quickly overview some of the challenges that we had to solve along the way. GraphDB, just like any other DB, is a subject of CAP theorem, in according to which a data store can provide not more than 2 out of 3 guarantees. In case of Neo4j, those guarantees are consistency and availability. So we had to give an answer. Would we be okay without partition tolerance? And the answer was yes, but under certain conditions. The point is that without true sharding, the only way to increase your throughput, particularly write throughput, would be through vertical scaling. So you have to know the limit of your system. If you under-provision your system and the number of events exceed processing capability, your system is going to fail. If you over-provision, targeting peak conditions, you're going to overpay for your hardware, you're going to overpay for license. For us, it was important to find that sweet spot with which we could live in terms of data processing. But at the same time, the nature of data coming to our system is having peak and valley nature. Sometimes it could be just avalanche of data, and sometimes could be barely couple 100,000. Therefore, we had to adopt throttling, but if the data are arriving faster than we can process it, we have to put a buffering mechanism in place. And with this buffering and throttling mechanism in place, we make sure that we are getting maximum from our investment, from our licensing cost and from our hardware. Our Neo4j server or cluster is constantly busy about 60 to 70% of CPU and memory utilization. Another problem that we had to solve is that, as we all know, all write transactions in Neo4j are executed against leader core. And leader core can be quite busy. As a matter of fact, pricing platform is quite very write-intense operation. And without true sharding, the only way to increase your throughput would be via vertical scaling. But vertical scaling can only provide you with a temporary relief. Ultimately, with the nature of business and volume of data growing, you will still hit the limit. So there must be some strategy to deal with ever-increased data volume. Fortunately for us, there was an answer. Data at Dell has a very well-defined, clear geographic boundary. And since we didn't have access to true sharding, we were able to organize so-called logical sharding. That means that each region would store only data that belong to that very region. And with some small subset of data would be duplicated between regions. And as a matter of fact, with this architecture, we still avoid proliferation. Original event from the upstream system still arrives only once. Then each region would pick event of interest to process within that cluster setup. And having Neo4j or Graph as our backend allows us to achieve true data-driven solution. All that sounds like a good marketing slogan, but what does it mean in reality? Data at Dell has two distinct set categories of property. First category of property defines relationships between price forming elements and the product structure. Those kind of semi-static data in its nature. However, the fact an adjustment gets associated to a product does not mean that it plays immediate role in its price calculation. It's nothing more than just a runtime candidate. Then during the runtime, a customer supplies an additional information, contextual information, and that's what finally is driving the decision what is applicable and what is not. This way we can afford logic like this. The same product, for example, laptop sold separately versus laptop sold along with some other product will have different price, kind of bundling logic. And since our focus is graph, let's quickly overview first category of properties that drives the relationships. Typically, business author association between price forming element and the product structure in the form of a Boolean expression tree. When we receive that element, we refer it as a condition expression. And originally, we were trying to preserve the natural structure of that Boolean expression tree. But very quickly, we found out that in this case, traversal logic becomes rather complicated. So we had to simplify. How we did so? We passed a Boolean expression tree through disjunctive normal form. This way, the complex hierarchical tree structure becomes a flat list of AND clause combined by OR clause. This way, if at least one AND clause is satisfied, the adjustment becomes associated with the product. But ultimately, all we want from our graph is two answers. For given product, give me all the adjustments. For the given adjustments, give me all the products. And let's quickly review some of the lessons that we learned along the way. Some of those may be self-explanatory or even obvious, but still we didn't notice that until a real-life situation pointed to them. For example, as I mentioned, pricing platform is a very write-intensive operation. And in Neo4j, all write operations are executed against leader core, which means our leader core is constantly busy. However, on the other hand, read transactions are not coming for free either. However, by explicitly declaring type of transaction, read transaction versus write transaction, we can redirect our read transaction to less busy instances. This way, we can give more breathing room to our leader. And on top of that, read replicas can be scaled horizontally for the read transaction. Neo4j is the most efficient when the entire content can fit within the core's memory. In our case, we store in Neo4j or bare minimum of information required to resolve the association between price forming element and product structure. Any additional information required for the e-commerce is stored elsewhere, Mongo, Redis, or some other store. This way, we again utilize our Neo4j setup to its max efficiency, and we don't waste our CPU cycles for paging. Another capability that I particularly appreciate within Neo4j is the fact that we can assign multiple labels to vertices and edges. And while it sounds like a simple capability, it is a very powerful mechanism, because all data arriving to pricing platform goes through data decomposition where we can infer additional information to be applied to that data. And this way, data that belong to the main schema or main content can be differentiated from the data that was inserted as a part of ad hoc case. Depending on the label applied, it can be seen as a part of the main content or part of ad hoc content. We all know that Neo4j consider write operation successful if majority of cores confirm that success. However, that doesn't mean that read replicas are participating in the confirmation. As a matter of fact, read replicas are getting information at some later stage. But how do we know when we hit the read replicas that that read replica has newly inserted data? And the answer is bookmarks. When we execute write transactions, we get back bookmarks. Pass those bookmarks to your read transactions, and if you happen to hit read replica that has not received yet the newly inserted data, it will make sure to hold your request until data arrives. And another tip that we learned kind of hard way is that in order to increase availability, we are using stretched cluster setup. All that means that cores are running in the physically separated data centers. However, not all data centers are equal. Some data center can be slower than another one. At the same time, Neo4j cluster select leader through the election process. So if your leader happens to be elected in the slower data center, your entire write experience will be less than satisfactory or lesser satisfactory. Fortunately, Neo4j allows us to provide an instruction to disallow certain cores to become leader. They still will participate in the election, but will not become leader themselves. Sounds unfair, but it's a very useful feature. And a few words about our migration strategy. While analyzing effort required to migrate the data from the legacy DB into Neo4j, we quickly found out that direct load would not be possible. And the reason being is that there's a lot of additional inferred information that was enriched during data decomposition phase. On the other hand, creating a migration tool would not be practical either, because in order to achieve that satisfy the data enrichment processes, we would have to duplicate the entire decomposition within that migration tool. And given the fact that migration tool, it is kind of throwaway investment, we decided to go with a different approach. Here I need to mention that all data coming to the pricing engine arriving in its canonical format, not schema, just a format. But on the other hand, upstream system or data supplying system have no knowledge about what is the canonical format, and honestly, they don't care. To address the discrepancy between the two, we have a set of microservices who are responsible to converting from native format into canonical format. So our approach was we extended our adapters to operate in the crawling mode. All that means, instead of waiting for an event to arrive, adapter would go to the data source directly and grab all available information and passes it over for processing to the pricing engine. This way, the entire processing is like inserting new data. Of course, we had to scale out to maximum our cloud functions, executing decompositions, and making sure we don't kill our Neo4j with the number of writes transactions and number of connections. And once the entire big bang load event was over, adapter would go to its normal operating mode, where they receive the event, process it to the canonical format, pass it over. This way, the difference between data migration and normal operation mode is just volume of data. Speaking of volume of data, anywhere per day we serve between different regions, anywhere between 1 to 50 million events. Each of those events end up some sort of presentation on the graph level, creating vertices and edges. It doesn't have to be every time new vertices and edges. It could be just update on an existing information. About 80% of those small payloads are small, which end up not more than 4 or 5 vertices and edges, which are typically representing price forming elements. About 15% are medium loads, where the number of vertices and edges can go up to 14, and about 5% are representing the actual products, where the number of vertices and edges can go up to 4,000. As you can imagine, each of those payloads has meaning, has impact, has value, and therefore we must guarantee zero loss processing system. How that was achieved is a separate subject, but one thing we can mention for sure, that without bulletproof infrastructure stability, that would be a very hard objective to reach. So let's quickly overview how we manage our infrastructure. Do you know, Raj?
Hi, my name is Natraj from database engineering. I work with Andrew and Bhanu. My role and responsibilities include evaluate application requirements, come up with the infrastructure and database capacity requirements, and set up the environments, and support the production and non-prod environments, ensure high cluster availability, and do the query performance tuning. The infrastructure picture shows 7-node the Neo4j deployment architecture with the geographically separated cluster, this one, to ensure that availability, and with horizontally scalable capabilities. We have set up a 7-node database architecture with 3 core nodes and 4 read replicas, and we configured the server groups to keep the core writes within the high performance data centers. Over to Bhanu.
Thank you, Natraj. Good afternoon, everyone. This is Bhanu. I'm also one of the database engineer at Dell, responsible for managing the Neo4j environment. Today, I'm going to talk about how we are monitoring our Neo4j clusters. Basically, we are using 2 different tools for this. First one is Splunk. This is how it works. Basically, we ingest all Neo4j logs into Splunk in real time. From there, we built multiple custom dashboards using multiple macros in the background. These dashboards will also get updated in real time. We use these dashboards for the real-time log analysis. On top of that, we created multiple alerts based on a specific keyword in the log. So let's say if one of the Neo4j node went out of memory, we get an alert. Let's say if there is an authentication failure happening on one of the node, we get an alert. So like that, we configured multiple alerts. Now let's take a look at how we are monitoring our OS and host metrics. For this purpose, we are using Prometheus and Grafana. Both host and database performance metrics will get uploaded into Prometheus every 30 seconds. And then we built 2 custom dashboards, one for operating system metrics and one for DB metrics. Operating system ones collects all the like CPU, memory, disk, network, and all that stuff. When it comes to DB metrics, it collects 40 different metrics related to Neo4j, anywhere from like connections, transactions per second, or database size, all that stuff. Finally, we configured Alert Manager to send out email alerts for any of the critical metric that stays above a specific threshold for more than 15 minutes. So just to conclude, we are using Splunk for the real-time log monitoring and Prometheus Grafana in order to perform the root cause analysis. With that, I'm going to hand over back to Natraj.
This slide explains about the Neo4j the database backups we take in the production environments and the non-prod refreshes. We have configured on the Linux. All these database servers run on the Linux. We configured the cron jobs. These are the scheduled jobs. They take daily backups, the full snapshots. We back up to the BoostFS. There the data dedupe things will happen, and it compresses the backups and save the space on the disk. And we configured the Delphix. Delphix is the tool we use to refresh the non-prod environments. It is a time-based snapshots. It takes backups like for every 5 minutes, and it keeps ready for the development teams to refresh the non-prod environments to the production copy. What they can do is they can refer to any snapshot to refresh their non-prod environment to complete their testing. They can set up the test cases and for any defect fixes, code fixes, or new code deployments. Then they can refresh their environments multiple times using the snapshot. The whole process is automated process. It runs on its own. It is a click. It takes care of the refreshes, the non-prod environments. Over to Naidu.
Thank you, Natraj. And basically, all we just discussed are good as an academical concept, but the true question to answer how business benefited from all those changes. And I can outline just a couple of benefits. First of all stakeholders within the commerce domain can get access to universalized data in presentation. That means that in the past, each region and each segment would have their own implementation of the pricing solution. With the pricing platform implemented under SaaS principle, this is no longer the case. The discrepancy between authoring concern, shopping concern and transaction concern is no longer the case. Time to market remains a major factor to stay competitive. About 90% of all cases we are addressing by leveraging existing capabilities using self-service configuration. And for the remaining 10%, we are adding capabilities later. This way, in 90% of cases, we don't redeploy the code, we don't do modification. This way we save on labor and maintenance. But probably the most important factor that we achieved through our re-architecture is that we decoupled price authoring concern from pricing calculation concern. In the past, business would have to reach to backend team and ask, we are planning to launch a campaign. Would you be able to support such a scenario? The answers would be yay, nay. Now this is no longer required. Business can go with whatever price authoring logic that can imagine. We are leveraging self-service capability using declarative syntax to create that type of association and resolution. We provide them with the what-if scenario and true delta calculation. And in terms of platform stability, we got more predictable SLA because we eliminated dependency on any external services. And on top of that, business no longer needs to coordinate data load effort with us because our systems allows for virtually unlimited horizontal scaling where it is possible and makes sense. And at the same time, for services that don't support horizontal scaling, we ensure throttling and buffering is in place. And with this, we are pretty much for today, unless we have some questions.